In this video, we're going to talk a little bit about numerical simulation, and we're going to discuss it in the context of an RC circuit, specifically the RC circuit that we saw in a previous video. So let's redraw that circuit, and let's say that we have some input voltage, which we call Vin, and we had a resistor of resistance R, and a capacitor with capacitance C, and we had some output voltage, which we called Vout. We went through and we showed that the governing equation for this problem is dVout dt plus 1 over RC times times Vout is equal to 1 over RC times Vin. And we showed that, for example, if we were to input a step function that looks something like this, we'll call this Vin, that out of it we would get some function that looked something like this. There's a decaying exponential in there, which is what you expect out of first order ordinary differential equations. It's possible to show that if you put in, and those of you who've had ordinary differential equations will have seen this, if you put in a sine wave like this for Vn, then you might get out, depending on what the frequency of that sine wave is, you might get out something that looks like this, which is another sine wave that has a diminished amplitude to it, and it may be shifted in phase. The peaks don't line up as they between Vout and Vin. So the next question is, well, what if we have something more complex than just a step function or a sine function? What if we have an input that looks something like, something really crazy? What if it just goes all over the place like this? Well, there are techniques that you can use in differential equations to come up with a solution to this. They range in complexity depending on the complexity of your input. But honestly, at some point it gets really difficult to do the math on paper, and there are plenty of problems out there, plenty of math problems out there for which there is no solution that you can write down on paper. And one of the things we do is we turn to numerical simulation. So let's switch gears for a second and think back to when you were first studying calculus and learning about derivatives and how you defined what a derivative actually was. Let's say that we have some function, we'll call it f, and it's a function of time, and I'm going to write out time here because we're going to call points on this function f of t at some point here in a second. And this has some arbitrary shape. We don't exactly care what it is, but when we wanted to define what a derivative was, we took 2 points on this curve at 2 closely spaced time intervals. And we're going to say that we took this one at time t, and we're going to say we took this one at time t plus delta t. And that means that over here, that this is equal to, let's see, f of t plus delta t, and this one is equal to f at t. And what you did is you said that the derivative of this curve is going to be is equivalent to the slope. And so we can find the slope by rise over run in this case, and we can say that the slope is equal to f at t plus delta t minus f at t divided by, well, we'll write it all out here, t plus delta t, the time difference, minus t, so that's just going to be f at t plus delta t minus f at t over delta t. And we define the derivative by saying the derivative of f with respect to time is defined as the limit as delta t goes to 0 of in fact this exact expression here, which is f at t plus delta t minus f at t. And you probably spent a fair amount of time doing proofs and figuring all this out. Now, a computer can't calculate things as the limit goes to 0. A computer, if we're doing numerical simulation, we can only do that simulation at specific points in time. So we must discretize our function, which means take it from being continuous to only dealing with certain points in time and defining the relationship between those points. So instead of, let me try to explain this graphically here, instead of having f of t here and t here, instead of a computer knowing what f of t is at all time, we only know what it is at certain points in time. And we can say, for example, that this is at sometime delta t. We'll call this 0 here. So that this is sometime delta t, and this is f at delta t. And this is sometime, this is sometime 2 delta t, 3 delta t, etc., etc., etc. And in general, we can just call these k delta t, where k represents all of the integers in 1, 2, 3, 4, up to however many bazillion you want to use to do your simulation. So that means that instead of defining derivatives as a difference as delta t goes to 0, as the limit goes to 0, we're actually going to go back to the expression where delta t is not 0, but is some small number. So for example, in our equation that we used for the RC circuit that we derived, so we're going to define the derivative, instead of being continuous, we're going to define it in terms of V out at discrete points in time. Specifically, we're going to define it as V out at some time step k